During this lesson, you will learn about the functions and components in a typical yaw damper system. You will then be shown how a yaw damper is operated and the indications and controls on the flight deck. Dutch roll is due to an angular disturbance about the vertical yaw axis, which causes an oscillation about the longitudinal roll axis and becomes worse with altitude. Dutch roll occurs because of a disturbance in the vertical yaw axis, which increases lift on the forward-going wing due to its increased forward speed and its relative wing growth, compared with a decrease in lift on the opposite wing. This induces the aeroplane to roll about the longitudinal axis. Due to this, the upgoing wing suffers from an increase in lift-induced drag, while the downgoing wing gains from a reduction in drag. This causes the aeroplane to yaw about the vertical axis in the opposite direction. So the whole cycle starts again, and this is known as Dutch roll. Having just learnt about Dutch roll, we will now need to look at a way of countering its effects to make flying a little more comfortable for the crew and passengers alike. There are numerous things we could design to try and counter Dutch roll, like increasing the size of the fin, but the negative effects of these changes outweigh their benefits. So what is needed is a self-contained inner-loop stabilization system, like an autopilot inner loop, which is independent of the autopilot and is known as a yaw damper. The yaw damper is classified as a separate system and uses small 3 to 6 degrees rudder inputs to counter the disturbance about the vertical axis. In some aeroplanes, the yaw damper is classed as the third axis of control for the autopilot, while in others, it is in addition to the third axis control. The yaw damper is normally switched on prior to departure and switched off after landing, and is invariably duplicated for redundancy. The yaw damper system can be co-opted into the autopilot when engaged to provide such functions as turn coordination and runway alignment during autoland. The first component in the system is the yaw rate gyro, which detects the angular rate disturbance of the aeroplane in the vertical axis and passes the signal to the phase advance. The phase advance enables maximum yaw damper deflection, which is between 3 to 6 degrees rudder deflection, to be applied at the point of maximum yaw rate, and ensures that the rudder input is moved faster so that the yaw rate is not accelerated. The signal is passed through a demodulator, which converts the signal to a DC signal where the output polarity represents the AC signal input phase. The signal then passes through the bandpass filter and then the modulator, which restores the AC signal, maintaining the appropriate phase. We will look at these last three items, which form the Dutch roll filter, in the next scene. The system as described so far would react to a normal coordinated turn as an unwanted yaw input, and would apply opposite rudder to counter the coordinated yaw demand. If we look at the output from the yaw rate gyro in a coordinated turn, it can be seen that apart from the roll in and the roll out, the signal remains constant. Whereas the Dutch roll output, which is a very low frequency, is constantly changing as the aeroplane yaws and rolls about its planned flight path. So the Dutch roll filter is a narrow band pass filter that filters the signal produced by the yaw rate gyro and only allows those associated with Dutch roll to proceed through the system. The Dutch roll filter has an input from the central air data computer, which supplies indicated airspeed. This is required as the yaw damper signal for a given rate of oscillation is varied inversely dependent on the airspeed. To recap, the signal has come from the yaw rate gyro through phase advance, being demodulated, passed through the Dutch roll filter, and then sent to a modulator. The signal now arrives at summing point 1, labelled SP1, which also has an input from an inverting integrator, int1, which cancels any signals from the amplifier until the system is switched on when relay 1, RL1, becomes de-energized. For the yaw damper system to work, we need a supply of hydraulic fluid, and this is made available through an engage solenoid, which ensures that hydraulic pressure is available at the transfer valve. The signal from summing point 1 is amplified and passed to the transfer valve, and this directs hydraulic fluid, which moves the yaw damper actuator. This mechanical movement is directed via mechanical summing point 3, which applies yaw damper input in addition to any rudder input to move the main rudder actuator, which moves the rudder. The linear variable differential transformer, LVDT, senses the movement and sends a feedback signal to SP1 via SP2 to nullify the input from the yaw rate gyro. This signal also supplies the information to the trim indicator to show rudder movement caused by the yaw damper. If a strong crosswind is present, the feedback signal may not be strong enough to centralize the rudder, so the signal is sent through relay 2, RL2, to an integrator, int2, which increases the signal strength to drive the rudder back to its central position. In some aeroplanes, depending on their Dutch roll characteristics, a failed yaw damper will either stop the aeroplane departing or cause a restriction to its maximum operating height. Some aeroplanes are fitted with test switches to test the system, normally during the post-engine start or taxi checks. Other aeroplanes use the natural yaw action of turning during taxi out to check the yaw damper function. As well as yaw damping, the system can be used to aid the pilot when an aeroplane suffers an engine failure. The yaw damper will sense the yaw towards the dead engine and apply opposite rudder to counter most of the yaw effect. The system could also be used to aid in turn coordination by applying a coordinated rudder input. The controls and indications for a typical yaw damper system are fairly simple and consist of the test switch, which we covered in the previous scene, and an on-off switch, which turns the system on or off and is used to isolate an inoperative yaw damper system to avoid spurious rudder inputs. There is a warning light which illuminates when there is either a fault in the system or loss of hydraulic or electrical power, and the indicator which shows the action of the yaw damper on the rudder. During this lesson, you have learned about the yaw damper systems and the reasons they are used in aeroplanes, which is to suppress Dutch roll. You examined the components of a typical yaw damper system, including the Dutch roll filter. Next, you observed the yaw damper in operation, including the test function and the way it can assist during engine failure and normal coordinated turns. Finally, you learned about the controls and indications in the cockpit.